Hello and welcome. In this presentation, which is part 4 of topic 3, where we look at asymptotic estimation of an unknown input in the presence of multiple unknown inputs. What we're going to do is we're going to ask the following question. What if the output measurement y of t does not exist, such that the following condition holds? Now, in our previous presentation, we were looking for an output measurement y of t, such that this condition holds. And if it holds, then we can actually explicitly, analytically express it in this seamless form, where it's contain the first derivative of measurement yi of t. In other words, we use only one output differentiator. So what happens if it's not satisfied? What are we going to do? The first answer to this question is when we decouple, or when we do the decomposition to get d1 of t, it must contain more than one first derivative of one output measurement. And so the natural question that arises here is how to design a node input observer with the least number of output differentiators. So what is the minimum number of output differentiators that we can employ? That will give us a good outcome, because that will still give us a simple observer structure with the minimum number of output differentiators. Even though we can't use one output differentiator, we want to use the minimum number of output differentiators. Okay, so we're going to address that issue. And so we kick off with a worst case scenario. The worst case scenario is where we need to have Q output differentiators. Now Q is the number of unknown inputs. So in this worst case scenario, we're going to employ Q output differentiators. So we take Q output measurements from the P output measurements. And then we have to employ them. We have to take the first derivative of them. Now, this situation is where the matrix T, we see the state transformation matrix, it has to contain the entire matrix D in there. Okay. So we're going, instead of like in the previous section where we just pick one output differentiator, in here we have to include all the columns, the entire matrix D. And the matrix V contain again the entire matrix D in there. So if we want to have this matrix V invertible, to do the matrix decomposition to obtain the unknown input in its entirety, D1 in its entirety, and the rest of the Q unknown input, then we need to have the observer matching condition actually hold true. So in other words, the rank of CD must be equal to Q. where Q is the number of unknown inputs. Okay. If that situation assumption is true, then we know that there always exists at least Q output measurements, such that this condition holds true. Okay, so out of the all the output measurements vector, there exists Q, at least Q output measurements. And so we call all of them as YQ of T. YQ of T is an output measurement vector that contains Q output measurements. And matrix CQ here is of rank, full rank, equal to Q. And then when we take CQ times D, that gives us a full rank matrix. So in other words, CQD is an invertible matrix. All right. So under this assumption, we pick Q output measurements such that this condition holds true. And then what we do is we rearrange the output measurement vector. So the first entry in here contains the output measurement YQ of T, this vector, and this is the remaining YI, the remaining output measurements. So when we look at this clearly, we require the number of outputs P to be more than the unknown input, which normally this assumption hold true here. Okay, so this is, remember, this is the worst case scenario. And so if that is the case, then we call this new arrangement the output measurement vector, and we call that it's just a new C matrix. All right. This C matrix is of dimension P by N, and Q is less than P. So in our decomposition, just like what we did earlier, we define this P matrix. By the way, in here, this C matrix is of the canonical form. And so we introduce this invertible matrix V to be basically that one there. And it is of this special form because of the way we pick matrix P. And if this is the case, then we can work out the inverse of matrix V, and we split that, or we partition that into two submatrices. We call it V1. Now V1 is this, has this structure here, which is the one down here. Now remember that V1 is of dimension by Q by V by N, by P, sorry. So this one is no longer a row matrix, but this is a matrix of dimension Q by P. And similarly, this V2 is of a proper dimension, which is P minus Q by P. Okay. Then we use this matrix T, which is the stack transformation matrix, and it's contain D here. And just like what we did before, we pick this metric E. Now, this dimension here is n minus q. It's not n minus 1 anymore because we include all columns of metric D in there. And so that's why the dimension of V1 is of Q by P. Okay. So we select E to be a rational basis for the null space of V1C. And if that's the case, and just like what we did previously, we introduce this stack transformation and then we decompose the system into a reduced order system. Now, in this reduced order system, as we can see, this is a disturbance-free reduced order system. Because the reason for that is we decouple, we obtain the unknown input vector. Every single unknown input is represented in this vector d of t here. And that's why this vi here is a metric of dimension q by p. All right. And this reduced order system is disturbance-free. It has the dimension of n minus q. And this output measurement vector is a linear combination of the original measurement vector, but it's of dimension p minus q. Okay. Now, when we look at this unknown input expressed in its own entirety, we can see that it's actually containing q output differentiator, q output differentiator. And it's also a linear combination of the stack vector, which is this reduced order system. So if we only need to estimate one unknown input, then what we do is we pick out the first row of this matrix, and we pick out the first row of this matrix, and that's where we use this notation to denote the first row of matrix X. If we are only interested in estimating one unknown input, which is the one of t, then it's given by this expression. It's just a single. This is just a single row matrix. This is a row matrix. And this is a single linear function of the stack vector. Okay? So when we do it, then we can then design a reduced order linear functional observer to estimate a linear combination of the reduced order stack system here, which is disturbance-free system. So that is a straightforward way to get the estimation of the unknown input d1 of t. Now, bear in mind that the first row of this metric V1 might have up to Q non-zero elements. And that's why we have to use first the derivative of Q output measurements. We can still compare to Howe and Muller. Remember Howe and Muller might ended up using P output measurements, output differentiators. Okay, so this is just an improvement over that, in the sense that we only need to use up to Q output differentiators, and we also design a linear functional observer instead of a full order, a reduced order stack observer to estimate the entire stack vector x bar 1 of t. On the other hand, if we want to, we can estimate the entire stack vector, the entire unknown input dt. The reason for that is because in our decomposition, which we obtain in here, is in the entire unknown input vector. And out of that, we have d1 of t up to dq of t. We were only interested in getting d1 of t. That's why we pick out the first row of it. And that's why we have this expression. And if we want to estimate the other unknown input, or all of them, it is possible to do. And it is just a matter of estimating this linear functional, which has dimension q, which is that combination there. And remember that in the decomposition, this submatrix is no longer a row matrix, but this is a matrix of q rows. And so overall, in this worst case scenario, we require the observer matching condition to hold true. And we come up with the estimation using Q output differentiators. Okay. We need the observer matching condition to be satisfied. And we design an unknown input observer to asymptotically estimate the unknown input using a linear functional observer. Okay, so the next natural question that arises here is, well, we were discussing the worst case scenario. Is there anything better than that worst case scenario? Like, what happens if we want to use the least number of differentiators to estimate d1 of t? And the answer is yes. In some cases, it is possible to do so. And so we then come up with the idea of searching for the minimum number of output differentiators that we can have in our decomposition of the unknown input d1 of t in its own entirety. All right. So that comes to this bit here, where we say, okay, let's seek for two differentiators. Now, what does it mean? It will be a bit clear later. What we like to introduce here is some sort of operation in here. So when we define an operation like the I column of matrix X and the J column of matrix X, we swap the positions. And this is the notation for that operation. Okay. So when we write that kind of notation down, that explains that column I position and column J, they swapped the positions. And similarly, here the I row of matrix X and the J row, they swap the position. Now, keeping in mind of this operation, what we're going to do is we're going to introduce some transformations. Okay, some stack and input transformation. So the first thing we do is we're going to rearrange some of the columns um, um, associated with metric D, which basically in turn associated with the way we arrange the unknown inputs through a metric Q. Q is invertible. And so in here we got this transformation. What it really is to swap the positions of the columns of metric D. Now remember, we only swap the Q minus 1 columns because the first column corresponds to the unknown input D1 of T, and we want to estimate it. So it's always first there. But we rearrange the columns. All right. And then we also introduce another transformation, which is symbol coordinate transformation. We call matrix M is invertible. And what is this transformation? Basically, we switch the position of the stack variables. We switch some of them, move them around, and then as a result of that, we can then change the rows of metric D. Okay, so bear in mind that we're going to do the column, swap in the columns, swap in the rows, so that this is the objective here. By the way, the metric C in here is of the canonical form. All right, so the idea here is we swap it in such a way that this new D matrix, we call it D bar. D bar is the result of switching the position of the stack variables, and as well as changing the columns. And so we let D bar, which is M times D times the inverse of Q, based on these two transformations. Okay. And if we can achieve the following outcome, where we got this sub matrix here, we call D bar 1, 1. Now, D bar 1, 1 has to be an invertible matrix. Okay, so we do whatever, but as long as we rearrange in such a way that we achieve this objective, and we got a block here, which is invertible. And the other thing is, this matrix D bar 1 is a zero matrix. It's a zero matrix. And then the rest of the submatrices, they are given by D bar 1, 2, is of dimension n minus 2 by 2. And this another submatrix here, which is called D bar 2. And if this is possible, then what it tells us is, oh, it's good. We can now need to use only two differentiators, to completely express the unknown input, D1 of T, in terms of the first derivative of two output measurements. Okay, so that's is the core essence of this arrangement. The swapping of the columns and the swapping of the rows of matrix D. So we introduce these two transformations based on this operation. Okay, based on this operation. And if that's the case, if we can do it, then we get the unknown input D1 in terms of two differentiators, two output differentiators. And then when we do the decomposition, after we rearrange everything, do all the transformation, metric T and metric V will have the first two columns, will contain the first two columns of this new metric D bar here. And then the rest of the decomposition can follow, and then we will be able to obtain the simplest form for the unknown input, which contains two output differentiators. Okay, so I hope that that is clear for the time being, that the search here starts with two differentiators. It's a matter of rearranging the columns, rearranging the row, and through these transformations. Okay, so important that we have two transformations. One associated with the stack vector, and the other one is associated with the unknown input vector. Now, so the next question is, what happens if this form can't be realized? That means that, well, we're not able to get, this one is an invertible 2x2 submatrix, and this is a zero matrix of dimension 2 by q minus 2. What we do? What do we do? The answer for that is, well, in that situation, we need to increase. We need to look for another output differentiator. We need to look for 3. Increase the number of differentiators. We meant output differentiators. Okay. And so we look for 3 output differentiators. And we go on to repeat the row and column operations until we achieve this new D matrix. Again, it's expressed in this form, where that block there is now an invertible matrix of dimension h by h. H is an integer number, which is the smallest integer number in the range from 2 up to q. We know that when up to q is and if the observer matching condition, how it's always possible, but we don't want that. We want it to be less than q. So that's the reason why we keep increasing the number of differentiators, and we look for the row and column operations so that we can achieve this new arrangement, where that one is an invertible matrix of dimension h by h. And the main thing here is this submatrix is a zero submatrix of dimension h by q minus h. And the rest of these submatrices, they are of appropriate dimension. So as you can see, if we can do that, then we can ensure, we can always guarantee that we have the least number of output differentiators that we can use for the estimation of this targeted unknown input. We don't have to go up to Q. That's the worst case scenario. If we're lucky, it can be within a range from 2 up to Q. And remember, because in this situation, the number of output differentiators is not reaching up to Q. So therefore, by this approach, we don't have to have the observer matching condition to hold. All right, so that basically explaining the situation. As you can see, we have a very simple way to search for the least number of output differentiator. When we can't find an output measurement to satisfy this condition actually. Not only that one, but the other one as well. So if we can't find it, that means that we have to use at least more than one output differentiator. So the question is, how many? The answer is no problem. Just do the following search for it, starting with two differentiators. Okay. And if we do the two differentiators, what we do is we just basically swap the columns, swap the row, looking for the arrangement, looking at the transformations, the two transformations, so that we can arrive at the new D matrix in such a way that this one is invertible and that one is 0. And if two differentiators not possible, we increase until up to a certain time where it is possible. And by doing this, we can ensure that we have the least number or the minimum number of output differentiators that we can use for design an asymptotic observer to estimate this targeted unknown input. Okay, so that basically the presentation for this part. It is based on chapter 3 in section 3.24. So thank you very much for watching. Please join me in the next video. We see topic 3 part 5, where we will show you with a numerical example. So we show how we can do the columns, the row swapping, and then as a result, we can yield the minimum number of output differentiator. Thank you very much, and I hope that to see you again in the next video. Bye.